Yeah, I think it's about time to start. So, welcome back, everyone. Great that you still showed up. This is the first talk of a new semester, and Keith Kearnes is going to talk about locally finite Schreier varieties. Please.
Okay, thank you. So my title is Locally Finite Schreier Varieties. And my co-authors are Michael Compatcher, Andrew Moorhead, Agnes Sendre. So we were talking, some of us were talking, and Andrew told me that Michael and he were thinking about Schreier varieties in a certain context. And then he said, we really don't know anything about Schreier varieties at all. And he started to enumerate various situations where they know nothing about Schreier varieties. And he happened to mention locally finite Schreier varieties. And my reaction at that moment was just to start sputtering, like, this is impossible. You can't have any non-trivial locally finite Schreier varieties. So we started thinking about it and came up with some interesting observation and a link to tame congruence theory. So that's really how I view this. Is what I'm talking about today is just an observation that links Schreier varieties and tame congruence theory. Okay, so let me just tell people where this began. Subgroups of free groups, an early theorem, I don't know the year, but it's due to Richard Dedekind, is that a subgroup of a free abelian group is a free abelian group. Okay. Jakob Nielsen, 1921, a finitely generated subgroup of a free group is free. So Dedekind's theorem has abelian in its hypothesis, and Nielsen's theorem has finitely generated. Both of those were dropped by Otto Schreier in 1927. He proved that a subgroup of a free group is free. Okay, we don't need finitely generated. And the abelian case is a separate question. This theorem was analyzed later by Peter Neumann and James Weigold in 1964. They characterized all varieties of groups that have the property that the subgroups of their V-free groups are V-free. And they found that such a variety must be the variety of all groups, or the variety of all abelian groups. That's Dedekind's result. Or there's another case that was not mentioned above. One of the varieties, A sub p, of elementary abelian groups of exponent p. That's the only thing that wasn't noticed by earlier people. So if you have elementary abelian groups of exponent p, they are definitionally equivalent to vector spaces over the p element field. And in this variety, every member is free. Every member of a variety like this is free of some rank. So every subgroup of a free member is free. Okay, this is just a vector space argument. So the interesting thing here is that these are the only examples for groups. And this leads to a definition. I will call a variety Schreier if subalgebras of relatively free algebras are free in the variety. Okay, and some people call these Nielsen Schreier, while others reserve the word Nielsen. A Nielsen variety will be a variety where the I think what I wanted to say here is finitely generated subalgebras of free algebras are free. That's what I wanted to say. Okay. All right, so that's a definition. There are a lot of papers on this. I would say from the early 60s till now, some of the focus has been on linear algebras. So these are some varieties of non-associative rings. They have a vector space structure and a bilinear operation. Okay, so it's known that the variety of Lie algebras is Schreier. The variety of all algebras over a field is Schreier. The variety of all commutative algebras over a field is Schreier. the variety where multiplication is 0, so constant multiplication, it's basically the same as vector spaces again, that's Schreier. So there are a handful of examples known, but not many. Not many examples are known. I'm going to call an algebra variety trivial if it satisfies the equation x equals y. X equals y says you have at most one element. Okay. Otherwise, an algebra will be non-trivial if it has more than one element. A variety will be non-trivial if it has a member of more than one element. Okay. When I talk about Schreier varieties, I always assume non-trivial because if it's a trivial variety, you can argue that every member is free. So every subalgebra of a free algebra will be free. There's nothing interesting to say in that case. Now I want to give another example that came after the working group theory. Trevor Evans wrote a paper characterizing the Schreier varieties of semigroups. Okay. A variety of semigroups is Schreier if and only if it's on his list. So the list of varieties he gave is variety of left zero semigroups, the variety of right zero semigroups, and he called the next variety the variety of constant semigroups. I think other people would call these just zero semigroups. All products are equal. These kind of look like pointed sets. That is, you have a set with a multiplication, all products are equal, so there's some special element in your set. All products equal that element. Evans calls these constant semigroups. The other case are the varieties of elementary abelian groups of exponent p considered as a variety of semigroups. These are examples of locally finite Schreier varieties. So that's what the talk is about. We're going to talk about locally finite Schreier varieties, and some of these illustrate what can happen. Okay. Now, one of the things Evans points out in his paper is there's some problem with the free algebra on zero generators. Okay, we want to say subalgebras of free things are free. So suppose I have a free algebra and I look at a subalgebra and it looks like a candidate for the free algebra on the empty set. Or maybe it is, maybe it isn't. We have to decide what is the free algebra on the empty set. So I put quotes around the word Schreier in Evans' theorem because he defines it slightly differently. He says the variety is Schreier if the non-trivial subalgebras of the V free algebras are free. So let me go back to the definition I gave. I just said a variety is Schreier if subalgebras of free algebras are free. But he says non-trivial subalgebras. And the difference is just, we're trying to avoid having to talk about the free algebra over the empty set. That's the point here. I'm going to quote what Evans writes in his paper. There is a particular reason for inserting the word non-trivial in our definition of Schreier variety. Without it, we would be forced to classify the variety of constant semigroups as non-Schreier. This is the variety of all semigroups with constant multiplication. Okay? Because any free semigroup in that variety contains an idempotent element that is the image of the multiplication map. It's a constant multiplication. Pick the element that is the image of multiplication. Idempotent here just means one element sub-semigroup. And that's, is it free? The question is this one element sub-semigroup free? It's certainly not a one-generated free algebra in this variety. The one-generated free algebra in the variety of constant semigroups has an element, let's call it x. And then if you multiply x by itself, x squared, you get the special constant. So you have two elements. You have the generator and the image of multiplication. So free thing on one generator has two elements. So the one generated sub-semigroup, which only has one element, can't be of positive rank. It can't be free of positive rank. Could it be free of rank 0? And now you have to decide what is the free algebra of rank 0 if you're in a language that doesn't have any constants. Do you say the empty semigroup is the free thing over the empty set if your language doesn't have constants, or is it the one element semigroup? So you can try to make an argument either way, but I think that when you don't have constants, then calling the empty algebra free over the empty set is better, because uniformly it's an initial object in the variety, and that won't be true uniformly if you just say, I want to look at algebras with no constants in the language. Then it won't always be true that the one element algebra is an initial object. Okay, but the empty algebra will be an initial object. Okay, so the one element semigroup will not be free in the variety of constant semigroups. So Evans just excludes it. And then he says,
but you could just add a constant,
right,
which might be more natural if you look at constant semigroups, that you give a name to the constant.
correct. And that's kind of what I'm going to say on the next slide. Not exactly, okay. But I want to move toward, there is an issue. There is an issue about constants and needs to be resolved somehow in your hypotheses, right? Okay, so yeah, so this is what Evans says. In the variety of constant semigroups, all non-trivial semigroups are free, so he wants to include it on his list, but technically the one element semigroup isn't free, so it could be a problem. And then he goes further and says, what is worse? We would have to classify the varieties of elementary abelian groups of exponent p as non-Schreier. Because again, as a semigroup, this vector space, it's just a vector space over the p element field, it contains a one element semigroup that is not named by a constant. So if you just look at elementary abelian groups of exponent p where your signature only has a plus operation, then you can generate minus by just, so x to the p is a constant term, x to the p minus 1 gives you negation. So you can generate terms that give you kind of what you want, but you don't name your singleton subalgebra with a constant symbol of the language. And he points out this is avoided in groups because we have a constant, basically. One element groups are free over an empty set if you have a constant in the language. Okay, so this is a technicality, but I'm going to tell you how I will handle that technicality. I will say a unary term operation is a pseudo-constant if its interpretation in this algebra is as a constant function. A unary term operation, if it interprets as a constant function, I'll call it a pseudo-constant. I don't think I'm the first one to use that phrase, that word, for this. Now I let P sub A be the subalgebra of A consisting of the ranges of the pseudo-constant unary term operations. That's a subalgebra. Now I go to the constants in the language, and I look at the subalgebra consisting of the interpretations of constant terms. Now we always have that if it's named by a constant, then there will be a pseudo-constant unary operation with the same range. There still will be a constant unary function with that same range. We always have this. And if there is a constant in the language, they're equal. The subalgebra of constants will be the same as the subalgebra of pseudo-constants if there is a constant in the language. But it can happen, there are no constants in the language, but there are some pseudo-constant unary term operations. And that's when you have a problem with the with the free algebra over the empty set. If you take an algebra that's free and it belongs to a Schreier variety, then each of these subalgebras must be free, but neither can be free of positive rank. And therefore, they must both be free of rank 0. So if you have some pseudo-constant, you must also have some constant. But as soon as you have some constant, the pseudo-constants and constants are the same. Okay? So I'm going to make this kind of assumption that if you ever have a pseudo-constant, then you have to back it up with a real constant. Okay, if you're dealing with Schreier varieties, that's a hypothesis that just lets you avoid problems with interpreting the free algebra over the empty set. So now I can tell you what theorem we have. Okay. So assume you have a non-trivial locally finite variety. If it has a pseudo constant, then assume, I'm going to go back to this so I can see my clock while I'm talking. I'm going to go back to this form of presentation. Yeah, if you have a non-trivial locally finite variety, and I assume that if it has a pseudo constant, it also has a constant. Okay, that's just this technicality. Then the following are equivalent. Let me just put it all up there. The variety is Schreier. That's subgroups of free algebras. Subalgebras of free algebras are free. It's equivalent to saying it's a Nielsen variety. Finitely generated subalgebras of free algebras are free. That's the same. And this is the part that interested me, that I thought was an interesting connection. Every finite algebra in V is a 0-1 minimal algebra in the sense of tame congruence theory. And that's equivalent to saying it's generated by a single finite 0-1 minimal algebra of more than 2 elements. Now, I'm not going to talk about Nielsen varieties anymore. Our paper has these as 2 separate things on the list, but I'll just focus on Schreier. And the kind of thing that I want to communicate is that what was surprising to me, that the Schreier property that's been around for 100 years has something to, it's connected in some way to tame congruence theory. And although we have very few Schreier varieties that have been discovered in the literature, you can generate lots of them once you know. They have restricted structure, but you can figure out exactly what they are in the locally finite case from this theorem. Okay, so I have to say what a 0-1 minimal algebra is. 0-1 minimal algebras. An algebra is 0-1 minimal or permutational if every non-constant unary polynomial function is a permutation of the universe. Okay, these kind of algebras made their appearance in a 1984 of Peter Palfy. He called them permutational. And then it turns out that as tame congruence theory was developed, these algebras were identified as basic structural units of that theory. Okay, so I'm interested in algebras. Here, I do not assume finiteness. Both Palfy and Palfy didn't quite assume finiteness. He didn't classify all the permutational algebras, but he classified all the finite ones, and he classified the infinite ones if they satisfy a special property called the bounded blocks condition. But I think it's still an open question to classify all algebras that meet this definition. In tame congruence theory, we just use finite ones, and they've been classified. Here's Palfy's theorem. A finite algebra is 0-1 minimal if and only if it's on the following list. List of algebras of size at most 2. Algebras that are polynomially equivalent to a G set for some finite group G. Or algebras that are polynomially equivalent to a vector space over some finite field F. Okay, now if you look at this, I hope that number 1 is kind of obvious. There's no algebra part in number 1. It's all combinatorics. That is, if you have an algebra and it has at most 2 elements, then any function from that set to itself will either be a permutation or be constant, because 2 is a small number. Okay, but when you get to 3 or more, then the algebra comes in, and Palfy was able to show that every algebra that has the property that it's non-constant unary polynomial functions or permutations must be polynomially equivalent to a G set or polynomially equivalent to a vector space. What that means for item 2, that on A, I can define a group action such that the polynomial functions of A are exactly the polynomial functions of the G set you get by letting that group act on the set A. Okay. And for 3, same thing. It's polynomially equivalent to a vector space means, first of all, you can find vector space polynomials in the clone of A, in the polynomial clone of A. You can find vector space polynomials, and all the polynomials of A will be vector space polynomials, and every vector space polynomial will have to appear. Okay, so this is a very strong theorem. It's a very, I mean, you have a very strong hypothesis as well, but I think everybody feels pretty comfortable with G sets and vector spaces. Maybe not algebras of size 2, but we have post-lattice. We can just refer to post-lattice to see what they look like. Okay. So the main goal I have is to persuade you that Schreier implies minimality, 0, 1 minimality, in the locally finite case. Okay, I'm not going to prove the main theorem that I posted earlier on an earlier slide, but I want to get what I think is the heart of the argument, that if you're locally finite in Schreier, then you must be one of these algebras. I mean, your finite members should be those algebras that appear on Palfi's list. Okay, so there's a lemma. There's a lemma we have to prove, and this is what does most of the work. I will start with a variety. It's locally finite and Schreier. And I pick a term. I assume it depends on its first variable. Okay, what does that mean? That means somewhere in the variety there's an algebra. And if you interpret this term and get a term operation, that term operation will depend on its first variable. And what does that mean for an operation to depend on its first variable? It means that there are 2 inputs that you can put into the operation, which give distinct outputs. And the only difference in the inputs is in their first position. So you put 2 things into the associated term operation. They only differ in their first position, but the outputs are different. Then the associated term operation depends on its first variable. Okay, pick any such thing. There will exist a term operation, a term in the same set of variables where the variety satisfies this equation. Okay, that's the main claim. If you have any term and it depends on its first variable, then I will say your term is left invertible in its first place. It's in the first variable, it is left invertible. There's another term you can compose with it in the first place to return x1, the first variable. Okay, the only hypothesis is V is locally finite in Schreier, and then you have this property of the terms. So let's see why. So I start with the n-generated free algebra in the variety. The n comes from the number of variables that appear in the term. Okay, the generating set I'll call capital X sub n. And now notice that if you take the term, you interpret it in the free algebra, you apply it to the generators, it will generate an element little t of the free algebra. Okay, and I'm going to generate a subalgebra of the free algebra with all the generators except the first. So S is a subalgebra of the free algebra. It's generated by x2 up to xn. Notice that S is free. It's a subalgebra of the free algebra generated by a subset of the free generating set. So it will be free over that subset. Okay, that's just algebra, I guess, or category theory. I don't know. Now, the assumption that the term depends on its first variable is equivalent to the statement that you will not generate the element t when you form this S, the subalgebra generated by x2 to xn. See, if t was in S, it would be generated by x2 up to xn, but that would say that t could be rewritten as a t prime of x2 up to xn without the x1 appearing. And with that happening, then it's impossible that t could depend on x1 in the variety. So if t was in S, it wouldn't depend on its first variable, because the only things in S are the things that depend on the later variables. And if, so that says if t was in S, and if t is not in S, then of course it must depend on its first variable, because if it didn't, I could reset the first variable to x2, it shouldn't change it, but then it would be in S. It would be generated by x2 up to xn. So the fact that t depends on its first variable means it didn't get generated when we created S. Okay, so it's not in the subalgebra generated by the last n-1 variables. So let's create a new subalgebra where we take the last n-1 variables and add t, and we generate something extra. The last n-2 variables will generate S, but t was not in S, so if I throw it in, I will get a subalgebra capital T that properly extends S. Now I use my local finiteness and compare sizes. S is free on n-1 generators, so it's the size of the free algebra on n-1 generators. T is a proper extension of S, so it's larger. T is a subalgebra of the free algebra on n generators. So I have this comparison. Now I'm going to use the Schreierness. T is a subalgebra of a free algebra, so it's free. What's the rank? What can its rank be? If it's strictly larger than the free algebra of rank n-1 and less or equal in cardinality to the free algebra of rank n, the only possibility is that T is free of rank n. Okay, it's a subalgebra of the free algebra of rank n, and it is free of rank n, so it's isomorphic to the whole algebra. They have the same size. They have the same size. They're both free of rank n. They must, in fact, be equal. And if T equals F, that says the first generator in F must lie in T, and T is the subalgebra generated by the last n-1 variables together with this element T. So there must be a term which you could apply to these generators and generate x1. So there is some term whose interpretation in this free algebra satisfies this equality. This is an equality of terms applied to free generators. Whenever you have an equality of terms applied to free generators, it holds throughout the variety universally. It's an identity that holds throughout the variety. So we get the identity that we were looking for. Okay, that's the main idea, where you use local finiteness and Schreier together to show that any term that depends on a variable is in fact invertible in that variable. That's a kind of as soon as you hear that, you start thinking about Palfy's theorem, I would say. Let me just write it out to connect it to Palfy's theorem. I want to show that with this lemma, you can conclude every finite algebra is a minimal algebra. So I choose a finite algebra in the variety. I assume it has a non-constant unary polynomial. Any non-constant unary polynomial comes from a term. You interpret a term as a term operation. You plug parameters in for all variables but one. So you get a unary function. So I'm going to need some parameters from A. If you plug it into the associated term operation, you get a unary function. This polynomial is assumed to be a non-constant unary polynomial of A. Necessarily, T is a term that depends on its first variable. So the lemma, or main claim, says I have another term which will be left inverse to T in its first variable. So I take that term, and I plug the same parameters in for x2 up to xn, and I get a left inverse of the unary function p. So every unary polynomial, if it's non-constant, it has a left inverse. Okay, now we're on a finite set. If you have a left inverse, it's actually a true inverse. It's a left and right inverse by finiteness. It shows that every non-constant unary polynomial is a permutation, which is what we needed. Okay, so locally finite plus Schreier leads to minimal algebras. There's more to the theorem because they're equivalent statements. How do we go back? How do we know if we have a variety whose finite members are minimal algebras, it will be Schreier? So there is something that has to be discussed here. We have seen that any finite algebra in a locally finite Schreier variety must be 0, 1 minimal. In fact, this is also going to be true for infinite algebras. If you have an infinite algebra, you can just examine it and see it will still be true that every non-constant unary polynomial will be a permutation or constant. Same kind of argument, really. I didn't use, when I applied the lemma to A, I didn't use local finiteness. So that A could have been an infinite algebra. Okay, so how do you prove the converse? And I ask, why is it the case that if every finite algebra in the variety is 0, 1 minimal, then the variety is Schreier? Why is that the case? So I'm just going to outline it. I'm not going to give the details, but assume you have a variety where every algebra is 0, 1 minimal. Then there are 3 cases according to Palfi's theorem. One case is that the algebra has size at most 2. Another case is that the algebra is polynomially equivalent to a G set. And the third case is that the algebra is polynomially equivalent to a vector space. Now, I'm assuming every finite algebra falls into one of these 3 cases, but different algebras could lie in different cases. Okay, I can assume that maybe some A in the variety is a G set, and some B that lies in the variety might be a vector space, and some C might be a 2-element algebra. Okay, so this is where we find ourselves. What's the first stage in the argument that goes the other way? And the first stage is to show that only one case can occur. Okay, only one case can occur. If all the algebras in V fall into one of these 3 types, then only one type can appear in V. And the idea is a simple one. Let's suppose I have a 2-element algebra, like 2-element Boolean algebra, right? What if I had something like that? Then I just take A cross A. That's in the variety. And now it's a 4-element algebra. So it can't be in the first case. It must be in one of the later cases. But if A cross A is polynomially equivalent to a G set, then A also had to be polynomially equivalent to a G set. If A cross A is polynomially equivalent to a vector space, then A was already polynomially equivalent to a vector space. So I don't have to worry about the 2-element case anymore. Even if there are 2-element algebras, they must be polynomially equivalent to G sets or vector spaces. Okay. Next, what if there was a G set in my variety and also a vector space? Then I take their product. If A is a G set and B is a vector space, their product will be neither a G set or a vector space. And that can't happen because all the finite algebras are supposed to be 0, 1 minimal. So I uniformize all the types. Only one type can appear. And that tells me that in my variety, either there is a finite group such that every finite algebra in V is polynomially equivalent to a G set over that group, or there is a finite field such that every finite algebra in V is polynomially equivalent to a vector space over that field. Okay, so this is just, stage 1 is just uniformize the types that can appear. And once you've done that, you have to know, what can I say about the clone of a variety if it's locally finite and all the members are polynomially equivalent to G sets? What can the clone look like? And there are just very few cases. There is more than one case, but there are a few cases. If I in number 2, what does it mean if my clone looks like so all algebras in the variety are polynomially equivalent to vector spaces? Then this is just an affine variety over a finite field. And there are just very few cases for the clones. Okay, so you study those cases, and studying the free algebra structure is very similar to studying the free algebra structure just for an ordinary variety of G-sets or for an ordinary variety of vector spaces. For a variety of vector spaces, as soon as you pick the field, every algebra in the variety will be free. Okay, if it's polynomially equivalent to vector spaces, they don't all have to be free, but it's very, very close to vector spaces, so you can make the argument work. In the case of G-sets, it's not true that in a variety of G-sets, every algebra is free, but if you examine what can they look like, you have the free G-set on one generator, and for higher rank, you just take disjoint unions of copies of that. And any subalgebra is just the disjoint union of some subset of those copies. It's also free of smaller rank. Okay. All right, so this is not hard to go the other direction, but this is a slog. You have to check some cases and cite the literature in some places about clones of affine varieties and clones of G-sets. Now, I want to end by just discussing something that came up as this was all being written, that there is another variation on this problem where tame congruence theory has a connection. And the variation is, instead of talking about Schreier varieties, so Schreier varieties are those where subalgebras of free algebras are free. There's a somewhat related question. If you have a variety, when is it true that projective algebras are free? Okay. When is it true that projective algebras are free? There's a whole nother community talking about this problem. What can you say about a variety if all of the projective algebras are free? So projective algebras can be shown to be retracts of free algebras. And if they're retracts of free algebras, they're isomorphic to subalgebras of free algebras. So certainly, if all subalgebras of free algebras are free, then all projectives will be free as well. But not all subalgebras of a free algebra are projective. There can be a wider class of varieties where projectives are free, even if not all the subalgebras of free algebras are free, the projective algebras might still be free. Okay, so this is discussing a wider class of varieties. And just repeat the argument that we did with small variations, and we don't end up with minimal algebras, we end up with what are called E-minimal algebras. Okay, go through the main claim, do everything exactly the same way, and you will see that the assumption that every projective algebra is free leads to the conclusion that all finite algebras in V are E-minimal. Now, here's what E-minimal means. A finite algebra is called E-minimal in the sense of tame congruence theory if and only if it is alpha beta minimal whenever alpha is covered by beta in con A. Okay, if you didn't already know what the definition was, then you're not going to learn it from what I wrote here. But let me just say this. This idea of minimality can be relativized to two congruences, alpha and beta, with alpha less than beta. And if you say it's minimal for all alpha beta with alpha less than beta, that's equivalent to saying 0, 1 minimal. So the minimal algebras we discussed before are alpha beta minimal for every alpha and beta where alpha is less than beta. But the E-minimal case, we only consider the alpha betas where alpha is covered by beta. So that's a weaker condition. weaker restriction to say E minimal, and it means the class of E minimal algebras are more general. So this is a more general theorem. I'm not assuming all subalgebras are free, just projective subalgebras, projective algebras are free. And I'm not trying to conclude that the finite members are minimal, but they are these more general class, these E minimal algebras. How more general are they? David Hobby and Ralph McKenzie have a chapter in their book telling us about the structure of E minimal algebras, but it doesn't give a very good description of the clone. Emil Kish has a paper from the 1980s in which he discusses the clones of E minimal algebras. So we know a little bit more about what E minimal algebras might look like, but they include nilpotent semigroups, P groups, and modules over finite local rings. These are examples of E minimal algebras. It's more general than the minimal algebras. So nilpotent semigroup somehow generalizes the G set example. And these P groups or modules over finite local rings, this generalizes the vector space type. Okay. If I restrict to the case of simple algebras, you'll see they agree with each other. Okay. So this would be a stronger theorem if we could prove it. We can't. We don't know a proof of this theorem. We know that the same proof we've given will show that if you have a locally finite variety where projective algebras are free, then finite algebras are E minimal, but we don't know how to go back the other way because we don't know if I have a variety generated by E minimal algebras, like generated by a P group. I don't know what the structure of the free algebras in that variety look like, and I certainly don't know the structure of the projective groups that would lie in that kind of variety. I will say that there's a famous theorem called Kaplansky's theorem from module theory, where he shows that if you take a ring R and you look at the variety of all R modules, and R is a local ring, then every projective is free. So that's called Kaplansky's theorem. Okay, so there is, at least in the abelian case where we're dealing with modules, the link between projective implies free on the one hand and modules over local rings that was already observed. Okay, so it inspires some hope that the converse might be proved, but to prove it you would have to know the structure of free algebras in varieties generated by E minimal algebras. I don't know that structure. Yeah, and this is what I think might be true. If you have a locally finite variety in which every finite algebra is E minimal, then every projective algebra is free. To do it, you need to know about the structure of free algebras in varieties generated by E minimal algebras. Okay, that's all I had to say. So I have my end of proof symbol here. Thank you.
Thank you.
Hmm?